What's up guys, welcome back to the channel. So today I'm here with another interesting standard DSA problem, which is first and last occurrences of X. This problem is asked by many companies guys, so make sure you stay tuned till the end of the video. Starting right away from the problem statement, so it says that you are given a sorted array ARR containing n elements with possibly duplicate is to find the indexes of first elements. So we are given an array which can have duplicate elements as well. Now the task is to find the first and last occurrences of an element x in the given array. Okay, one note is also given here. It says that if the element x is not found in the array, then you can return both indices as -1. When it says both indices, then it's basically talking about the first and last occurrences of x, right? So one example is given here, guys. Let me explain the problem using the given example. We have an array and the size of array is 9, right? Let me write the array. So I have first element as 1, then 3, then I have 5, 5, 5 and 5, then I have 67, then I have 123 and then I have 125, right? So this is the array given to us. Now the value of x for this particular array is equal to 5. This basically means that we have to find the first and last occurrences of the element 5 in the given array, right? So x is given 5 here. Now guys, first of all, let me write the indices of every element. So starting from the 0 index, because an array follows a 0 based indexing, right? So 0, 1, 2, 3, 4, 5, then 6, then 7, then 8. So now you can easily figure out that the first occurrence of 5 is this one and the last occurrence of 5 is this one, right? What is the index of first occurrence? 2. What is the index of last occurrence? Nothing but 5, right? So 2 and 5 is going to be the output for this particular example. Now I hope the problem is being clear to you. Let me take another example, guys. So first of all, let me erase this so that I can get some space, right? Let me write here. So now let me write one more example here. So let's say I have an array 1, 2, 3, 4, 5, and for this particular array the value of x is equal to 7, right? So guys, now you can see that this particular condition is true, right? Element x is not found in the array. So in this particular case I have to return -1 comma -1. Let me take one more example. So let's say I have an array 1, 2, 3, 4, 5, and the value of x is equal to 3. So you can see that we have only one occurrence of 3, right? So in this particular case, the first and last occurrence is same, which is index 2. So 2 comma 2 is the output for this particular example. Now I hope problem statement is clear to you. So without any further delay, let's talk about the solution now. Okay, so I have written one example here, and guys, after looking at the problem explanation, the first approach that will come to your mind is quite similar to this one, right? What we can do is we can simply iterate over the array and then we can look for first and last occurrence. But how we can look? Let me explain, guys. So I'm simply going to start a loop for I equals to 0, then I smaller than n, then I plus plus, right? Inside this loop, I will check only one condition. If my element, which is array of I, is equal to x, right? This is how I can look for every occurrence of like this particular like the element x in the array, right? So guys, question is how to check for first and last occurrence. Let's say I want to check for 2. So I can have two variables. First is the first occurrence, which is initially equal to -1, and the second is last occurrence, which is initially equal to -1, right? And I will check if my first occurrence is not there, right? If my first occurrence is equal to -1. In this case, I'll say that, okay, now the first occurrence is equal to the current index that we have, right? This is very interesting, guys. Let me explain. So I'll start with this particular index, which is 0. Then I will come here and this element is equal to the value of x, right? So condition will become true. And now I will say that there is no any first occurrence till now, right? So I'll say that first occurrence is now equal to this index, which is 1, right? After this, when I say this element again, so I'm not going to change the first occurrence, right? Because first occurrence is now not equal to -1. So this is about the first occurrence. But what about the last occurrence? So see, guys, initially I'm at this particular index 0, then I come to this index 1, right? So here I can see that I have one element 2. Till now I don't know about these elements, right? What are the elements I have after this 2? So I'll say that, okay, the last occurrence is this particular element index, right? So I'll say that, okay, last occurrence is equal to I again, right? After this, when I see this particular element, So I'll say that okay, last occurrence was not this one, last occurrence is this particular index, right, which is now equal to 2. So this particular like statement or this particular expression is going to override the last occurrence again and again till we reach this particular endpoint, right? So if there is also present the same element, so last occurrence will be overridden by this, right? So guys, this is how it works. Last occurrence is nothing but the rightmost occurrence, right? And we are moving towards the right. So this is the first approach that we have. Talking about the time complexity, so it is nothing but O of n here because we are iterating over every element, right? So guys, this is about the first approach that we have, but we can optimize it. We can use binary search because we are given a sorted array, right? So first of all, let me erase everything. I hope you have noted this down, guys. Now, as I said that this problem is based on binary search, but first of all, for those who don't know about binary search, let me give you an idea in brief wise. Let's say I want to search for this particular element, right? So what is the initial search space that we have? This is the search space, right? I have to search the element in this particular space. So what is the first index of this search space? First index is 0 and the second index is going to be 9, right? So guys, what I'm going to do is I will simply look for the middle element in this particular search space. Middle element I can simply find by, let me call it low and let me call it high index, right, which is the last index. So I'll say that okay, low plus high by 2. This is something which can give us the middle index, and guys, middle index for this case is going to be 0 plus 9 by 2, which is nothing but 4, right? I'm writing 4 because this is an integer division, so instead of writing 4.5 I will write 4, right? So what is the value of index 4? 0 1 2 3. This is the value at index, okay, this is the value at index 4, guys. And now I'm simply going to compare this value with this particular target value x, right? So there are three conditions possible. I'll say that the first condition is if my let's say this particular index is mid. Why I'm saying mid? Because I'm calculating the middle index only, right? So I'll say that okay, if array of mid is equal to x, then I have to do something. Else if else if uh, array of mid can be smaller than x also, right? Array of mid is smaller than x, and else if array of mid is greater than x. So these three conditions I have, right? These three conditions I have. So what I have to do in these three conditions, let me explain. So whenever the element mid is equal to x, so I'll say that okay, element is found, right? This is the condition where the element is found. If the element is not found, so for case you can see that array of mid here is something which is greater than this particular value x equal to 2, right? So this is the case that we have. Now guys, see, I want you to observe something here. If this element 4 is greater than 2, right? 2 is the target here. 2 is the target. So if this element is greater than x, then one thing is sure that every element after this is going to be greater than x, isn't it, guys? So there is no sense of searching in this particular space. This is something that we need to understand when we talk about binary search. So what we are going to do is we are going to search in this particular space only, right? Because there is a possibility that on the left side I will get a element which is equal or smaller, right? So in this particular case, I will do one thing. I'll say that okay, now my high will become mid minus 1, mid minus 1. And what will happen is now my high will move to this particular index, right? Mid minus 1. And now okay, this is my new high, and now I have to search in this particular space, right? This is my low, this is my high. So this is how we work, guys. And let me take another example. So let's say for any case this element is smaller, this element mid element is smaller, right? This was high and this was low, right? So this mid element is something which is smaller. Of course this is not smaller for this case, but let's say this is smaller. So in this particular case all these elements are going to be smaller on the left side, so there is no sense of searching in this space, so I will search in this space for that particular case, right? So for that case I have to do low equals to mid plus 1. This is how binary search work, guys. I have to perform this binary search while my low is smaller than equal to high, right? Why I'm not performing binary search for low is greater than high? There is a reason, guys. The reason is if low becomes greater than high, then the search space is not there, right? Because low is always the leftmost index and high is the rightmost. So the first case is low is equal to high where we have only single element. So now we have to get mid element as well, which is nothing but low plus high by 2. This is how the binary search work, guys. This is the code of binary search. If this condition has never reached while searching an element, then I'll say that okay, not found at last, right? Not found if this particular condition was not true and I have not returned the value. So this is about binary search. Now let me explain how we can use binary search to find the first and last occurrences of an element. Okay, so guys, now I have written the pseudocode for the binary search as well, right? And we are going to modify this code only. See, we are talking about first occurrence first, how we can find the first occurrence of an element. So let's say we are somewhere at this particular index, right? We are somewhere at this particular index and the value of x is equal to 4. So you can see that now we have found our element x, right? So we will come to this particular condition, right? Now our array of mid is equal to x. So we will say that, okay, this is going to be the first occurrence, right? This is going to be the first occurrence. So this is the first occurrence, which is mid, right? But you will say that, hey, why you are saying that this is first occurrence? Because first occurrence can be on the left side as well, and even you can see that this is the first occurrence which is present on the left side, right? So I will say that you are right. Well, whenever we found an element and we are concerned about the first occurrence, so there is a possibility that first occurrence will be on the left side, right? Because this is a sorted array. So we will say that, okay, we have to find the first occurrence, so we will move to left side. But as there is no guarantee, that's why we are storing this particular value first. So now we can move to left side. How we can move to left side? If this is my high index, so I can simply do high index equal to mid minus 1. If this is my high index, this is my low index, so I have moved to left side, right? So I'll say that, okay, just do high equal to mid minus 1. Mid minus 1. Guys, this is how we can find the first occurrence. At last, we just need to return first. And this is how we can get the first occurrence of an element x. And now in a similar manner, we can get the last occurrence as well. This is the code for the last occurrence, guys. In the last occurrence, we move to the right side. See, let's say I have found, first of all, let me remove this. Let's say I have found the element here which is equal to 4, right? And I will first say that this is the last occurrence, but there is a possibility that last occurrence can be on right side as well. So I will say that this is my last occurrence and I will check for right side as well, right? So this is my last occurrence and I'm checking on right side as well by moving my low equals to mid plus 1. So you can see that initially, okay, let me remove this. Initially low was here, but now low is pointing to this element. So if this is low, then this is the search space, right? This is how we can find the first and last occurrence, guys. Now I hope this is clear to you. I just want to talk about the time complexity. So see how it works. We have a binary search code, right? And this code basically divide the search space by 2 each time, right? So initially this is my low, this is my high. So let's say initially we have size of n search space, then we divide by 2, this is n by 2, then we again divide this particular search space by 2, which is n by 4, then we have n by 8 and so on, right? And we are going to stop when the operations become 1, isn't it, guys? So now I want you to notice something here. See, this is my first operation, this is my second operation, this is my third operation, this is my fourth operation, and so on. How many times I perform an operation? Let's say k. So time complexity is nothing but O of k, isn't it, guys? Now we just need to figure out what is the value of k, right? So this is a geometric progression, GP. So we can find the k term. K term is basically given by a of k in a GP is given by a r raised to the power k minus 1, right? What is the value of r here? R is nothing but the factor by which we are changing the value. So this is 1 by 2, right? So now a of k is nothing but 1. 1 is equal to, what is a here? A is equal to n. Then what is the value of r? This is 1 by 2 raised to the power k minus 1, right? So I'll say that, okay, n is nothing but equal to 2 raised to the power k minus 1. Now I can take log both side, right? So I'll say that, okay, take log both side, both side. So what this will do is this will say that, okay, log n equal to log 2 raised to the power k minus 1, right? And as this is log base 2, so now I can write this as log m raised to the power n is nothing but n log m, right? N log m. So it will become k minus 1 log 2 is nothing but log n, right? So now you can see that log this value is equal to 1. So I'll say that, okay, minus 1 is equal to log n, right? And now you can see that k is equal to log n plus 1. And guys, k is simply representing the number of operations that we have performed. This is first, second, third, fourth, and so on up to k, right? So we have performed k operations. So now the time complexity is O of log n plus 1. And guys, when I write this, then something beautiful happens. See, we don't consider constant when we write the time complexity, so the exact time complexity is O of log n, right? And we are not using any extra space, so space complexity is O of 1. So this is about the time and space complexity. Let me quickly show you the code, guys. So this is the code. This is the code in like Java and Python, and let me show you the code in C++ as well. This is the code in C++. You can see that, guys, first of all we are concerned about this first occurrence, then we are finding the last occurrence. The code is going to remain same as I have explained you. This is the main logic, guys. First I find the first occurrence. If my first occurrence is equal to -1, then of course last occurrence is also going to be -1, right? Because the element is not there, so I have to return this pair, else I will return this pair. This is the code in Java. Oh, my bad. This is the code in Python, guys. And this is the code in Java. So now this is all about this video. I hope you have understood everything. Thank